Let's talk about one of the most intimidating parts of any intro physics class, the kinematics equations. You know the ones. They look super complicated, right? But what if I told you the secret to really getting them has nothing to do with fancy calculus, and everything to do with some simple shapes you probably learned about back in middle school? Yeah, for real. Let's dive in.
Does this sound familiar? I mean, this is a real post from a student on Reddit, and it just nails that feeling, right? That moment of panic when calculus suddenly crashes the physics party. Well, if you feel this way, you are not alone. And I've got good news. You do not need to be a calculus master to understand these equations. We're going to build them from the ground up, no calculus required.
And here they are, in all their glory. This is the final boss. This is what you see in the textbook, just a wall of symbols. It feels like you just have to grit your teeth, memorize them, and hope for the best on the test. But what if we could actually build one of the most important of these, from scratch, using nothing but some basic geometry? Stick with me here.
Okay, before we try to take on that final boss, we've got to go back to level 1. So let's just hit rewind and look at the two fundamental ideas that all of this is built on. And the best part? You already get these. You use them every day, you just don't think about them like this. First up, velocity. You know, it's just how fast your position is changing. It's that simple. If you drive 60 miles in 1 hour, guess what? Your velocity is 60 miles per hour. It's just the change in your position divided by the change in time. Easy enough, right? And number 2, acceleration. All this is the change in velocity. When you stomp on the gas pedal in your car, your velocity changes. That's acceleration. It's the change in your velocity over the change in time. And believe it or not, these are the only two tools we're going to need to build everything else.
And now for the magic trick. Seriously, we're going to step away from all the abstract formulas for a second and just look at some simple shapes. This is where that big aha moment happens. This is where we can literally see the physics happening.
And you know, this brilliant idea actually comes from another Reddit user, Diggler G. Dirk. They pointed out that instead of wrestling with complex calculus, you can just look at a simple graph of velocity versus time. The shape that graph makes? Well, that shape holds the entire secret. Let's see exactly what they're talking about. So here it is. This is our graph. Up the side on the vertical axis, we've got velocity, and across the bottom, the horizontal axis, we have time. So imagine an object, it's starting with some velocity and then it starts accelerating at a nice, steady rate. That motion creates this straight, sloped line. Now here is the absolute key to everything. The total distance the object travels is just the area of the shape underneath that line. Now, this weird trapezoid shape might seem tricky to calculate, but we can break it down into two super simple shapes we all recognize: a rectangle on the bottom and a triangle sitting on top. Think of it this way. That rectangle's area, that's the distance the object would have gone if it never sped up, if it just kept its starting speed. And the triangle? That's all the extra distance it covered because it was accelerating. Okay, let's actually build it, piece by piece. First, the rectangle. Area is just base times height, right? For us, that's time, t, multiplied by our starting velocity, v1. Done. Now, the triangle. Its area is 1/2 times base times height. The base is t, and the height is the change in velocity. Now, remember our definition for acceleration? We can shuffle it around to see that the change in velocity is just a times t. So we do a little swap. We substitute a times tn for the triangle's height. So when we add our two areas together, we get the rectangle, v1 times t, plus the triangle, which is now 1/2 times a times t squared. And would you look at that? The equation we just built, displacement equals v1t plus 1/2 at squared, that is one of the big four kinematics equations. We just derived it with zero calculus, no weird integrals, just by adding a rectangle and a triangle together. See, it's not just a formula you have to memorize. It's actually a visual story about how something moves. So now that we've kind of peeked behind the curtain and unlocked the logic for one of these, the others don't seem so scary anymore, do they? They're all connected, all derived from those same basic ideas. So we can finally look at the full set, not as a challenge, but as what it really is, a powerful toolkit for understanding motion. And here it is, the complete toolkit. Now the most important thing to look at on this chart is that last column, missing variable. This right here is the secret weapon for solving physics problems. Each equation is custom built for a situation where you're missing one piece of the puzzle. So if the problem doesn't say anything about the final velocity, use the third one, the one we just built. If it doesn't mention time, you grab that last one. It's all about picking the right tool for the job.
So why does any of this matter? I mean, who cares? Well, because this toolkit isn't just for passing a class. It lets us describe, predict, and actually understand the motion of real things in the world all around us. These equations can help us figure out all sorts of stuff. You know, how tall is a building? How does a car brake? How does a puck slide? But let's use our new toolkit on something with slightly higher stakes. Let's see if a plane can land safely on a short runway.
Okay, so here's the problem. Picture this. A plane is coming in hot, touching down at 100 meters per second. The runway is only 800 meters long, and it's got to stop before it runs out. The brakes can slow it down at a steady 5 meters per second squared. So, the question is the runway long enough?
All right, let's play detective. What do we know? We've got the initial velocity, v1, that's 100. We know the final velocity, v2, has to be 0 because the plane stops. And we have the acceleration, a, which is -5 since it's slowing down. So what are we trying to find? The distance or displacement, s. We look at our toolkit. Which equation has all of those variables but doesn't have time in it? It's that last one on our list.
So we grab our tool. v2 squared equals v1 squared plus 2as. We just plug in the numbers. 0 squared equals 100 squared plus 2 times -5 times s. You just rearrange that a little bit, solve for s, and you get your answer. The plane needs 1,000 meters to come to a full stop.
So what's the verdict? The plane needs 1,000 meters, but the runway is only 800 meters long. So nope, it cannot land safely. And just like that, a couple of symbols on a page gave us a clear life or death answer. That's the power of physics right there.
So look how far we've come. We started with these scary-looking equations and discovered they were really just simple shapes in disguise. We turned them into a practical toolkit and solved a real-world problem. We've pretty much mastered motion in a straight line. But what about a ball you throw through the air or a planet orbiting the sun? What happens when motion isn't a straight line, but a curve? Well, that's the next step on the journey.